In the process equipment design subject, we are discussing the silent tube heat exchanger design. Okay, so basically the various parts we discussing already in the process equipment design subject in one in the semester number 6. So in the last we discussed the fluid allocations property. So it may be corrosive fluid, it may be fouling of the tube sheet, then fluid temperature, operating pressure. So steam temperature. So the next criteria should be selected by the main required by the design of silent tube heat exchanger. It is then steam temperature. A steam temperature should be decided by the designer. If they are not available for a specified, normally temperature of heat transfer medium should be decided by designer. Heat transfer temperature should be designed by the temperature should be defined by the designer. For coolers and condense temperature of cooling water, chilled water, brine are decided by the designer as per the application or as per the requirement of the or the application of the heat exchanger. Okay, so cooling medium and heating medium, that is decided by designer, which is coolers, condenser temperature, cooling water temperature, then chilled water, brine solutions. Okay, for heaters and reboilers, steam, high therm oil or draw therm oil temperature should be decided by designer. Then log mean temperature difference, that is delta T Lm. This will be already we discussed in the heat transfer subject. Delta LMTD, log mean temperature difference. So log mean temperature difference is calculated from these equations. D of Tm is equal to F of T D of TLm. D of TLm is the log mean temperature difference. So it will be written as a delta TLm equal to T1 minus T2 upon minus T2 minus T1 divided by capital T1 minus T2, then capital T2 minus T1. For counter current flow, if the flow in the heat exchanger should be it is in the counter current. So T1 is the hot fluid inlet temperature, capital, and T2 is the hot fluid outlet temperature, where small t1 is cold fluid inlet temperature and T2 is cold fluid outlet temperature, which is both are given here. Okay. And for the co-current fluid, the delta TLm should be in the form of this. Okay. Now F1, the temperature correction factor for 1 heat exchanger, 1 like a one shell and one tube heat exchanger, the temperature fraction correction factor, it is F of T is equal to 1. Okay, when cell side pass or a tube side pass are more than 1, when cell side pass and tube side pass are more than 1, it should be considered as a f of t is equal to f of rs, where r and s are the temperature ratio. So R is T1 minus T2 upon T2 minus T1, where the S is T2 minus T1 minus T1 minus T1. So it can be more uh, obtained from the graph than it is the f of t that can be obtained from the graphs. And this graph is available in the various books. Nature of graph is that f of t is less than 0.75, that is economic heat exchanger design can be not be achieved. જ્યારે ft ની વેલ્યુ 0.75 કરતાં શું હોય, ઓછી હોય, ત્યારે એનો મતલબ એવો થાય છે કે હીટ એક્સચેન્જર છે એ શું નથી કરી શકતું, હીટ એક્સચેન્જર ઇઝ નોટ can design achieve economic heat design. For such a case, alternate type of heat exchanger design should be considered. In the case where the temperature cross is likely to occur, multiple cell pass heat exchanger or more cell in series should be considered. So the nature of the f of t graph is shown in figure. So different curve for the difference value of r. Now heat duty balance or energy balance. So the heat duty can be calculated by mCp delta T. So mCp delta T, that is CPT, CPS and CPT. So flow rate of cooling medium and heating medium. So it is m of s for particular s, okay, and for T, so that is m of s CPS T1 minus T2. Then it will be the opposite of ms, that is m of t CPT D2 minus T1. The next parameter is that overall heat transfer coefficient. Overall heat transfer coefficient. So it should be considering as a assume U from the standard tube. U should be considered for the standard tube, and then it is the written as a standard table for various types of various case are available in various books on this subject. So find out the heat transfer based on the assume the heat transfer area. So overall heat transfer coefficient, so it is in the A is equal to Q by U of delta T. Okay. So range of 3 by 4 inch condensation and without phase change heat exchangers. So area is considering n of t p d0 into L. So L equal to the length and the which should be in the various size available, like Standard length is 6 to 8 feet, 12 feet, 16 feet. And numbers of tube, N of T is selected number of cell and side tube pass for the first trial. First one is one shell and tube, then 1 and 2 heat exchanger, that is 1 shell and 2 tube. Decide about the arrangement of tubes. Then after, the next part is that decide the arrangement of tube. So first choice of triangular arrangement. Find out shell diameter, okay, in Paris tube. So this one is only informative. Okay. Next is that calculation of tube side heat transfer coefficient. સેલ સાઇડની પછી આવે છે ટ્યુબ સાઇડ હીટ ટ્રાન્સફર કોફિશિયન્ટ આપણે કેલ્ક્યુલેટ કરવો પડે. So for without phase change, heat transfer rate is given in by this equation. Re is equal to di gi upon mu is equal to di into m dash divided by nt upon np pi by 4 di square into u, which is less than 2000. And the Sidertat equation we know that, which is given by the numbers, Nusselt numbers given by this equation, and hence there is a less than the value of 3.5 and it should be taken as a 3.5. So Nusselt number for the Sidertat equations we discussed, we know from the heat transfer subject ની અંદર આવે છે, બરાબર, જે સેમેસ્ટર નંબર 4 heat transfer subject ની અંદર Sidertat equation from the Nusselt number HIDI divided by KF 1.0686, Reynolds number, Predor's number to DI by L is 2.13. This one is only informative, but you have to remember this. And similar Ditus-Boelter equation is for Reynolds number which is greater than the value is 4000. So Nusselt number is HIDIKF C into Reynolds number raised to 0.8 and Predor's number raised to 0.33, and the other values are mu by mu w is raised to 0.14, and the value of C is in the range of 0.021 for gases, 0.023 for non-viscous liquid, and 0.027 for viscous liquid. And the M is the fluid viscosity at a bulk temperature, fluid temperature. And the MW is the fluid velocity at the tube wall temperature. And for the transitions relation, no reliable equation is available, and it is in the range of 2000 to in between the 2000 to 4000. So heat transfer coefficient is found by both equation 1 and 2. Okay, so the tube side pressure heat transfer coefficient without phase change heat transfer can be calculated by following equation: HIDI upon KF into J of H and the Prandtl number, Reynolds number and Prandtl number raised to 0.33 mu by mu w raised to 0.14. Okay, then second thing is that calculate the overall heat transfer coefficient. So this one is also we discuss in the heat transfer subject. Okay, so remember that U is equal to 1 upon H0 plus 1 upon H0D plus d0 into ln d0 by di upon 2 kilowatt plus d0 by d1 into 1 upon hid plus d0 by di into 1 upon hi. U0 is overall heat transfer coefficient based on unit surface of the tubes. H0 shell side heat transfer coefficient, that is watt per meter square. D0 di outer diameter and inside diameter of tube. Kw thermal conductivity of tube wall. HID inside fouling coefficient and HOD is the outside fouling coefficient. Okay. So and then required heat transfer area is Q by A0 જે પાછળ આગળ આવી ગયું છે એ પ્રકારે જ divided by U0 and delta Tm. So these are the 13 steps to find out the heat transfer, the design of silent tube heat exchanger.